Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this rectangle ABCD, and in the second question, we'll find out the area of this green shape that is inside square ABCD. So we'll start with the first question. In the drawing, we have rectangle ABCD. Inside this rectangle, we have this semicircle. In addition, we know that this is called AP, this is equals to 6 units in its length. This is line segment PC, this is equals to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, those four angles, they are all right angles because they are angles inside rectangle ABCD. And all the angles inside the rectangle are right angles. So this is right angle. This angle is also 90 degrees inside. This is also a right angle. And this is a right angle. So in the next step, we'll define the center of this semicircle. This point is point O. We'll define the radius of this semicircle as x. So point O is the center of this semicircle. Point A is the point on the semicircle itself. Therefore, OA is the radius of this semicircle. Is equals to x units in its length according to our definition. We define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. So OE is also the radius of this semicircle. Is equals to x. In the next step, we define the point of tendency of tangent DC with this semicircle. This point is point M, and we join points O and M together by a straight line. Point O is the center of this semicircle, point M is the point on the semicircle itself, therefore OM is the radius of this semicircle, is equals to x. And because of the fact that the radius OM is equals to x, the radius OM is known to point M, that is the point of tendency DC with this semicircle. And whenever you have a radius that is known to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can deduce the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total it must be equal to 360 degrees. According to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in size. So inside the small quadrilateral DMOA, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle in front of a square. So relate to this small quadrilateral DMOA, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DMOA, side MO must be equal to the opposite side DA, but MO is x, therefore the opposite side DA must be also equal to x units in its length. Likewise, in the big rectangle ABCD, the opposite sides must be also equal to each other. That is to say, side DA must be equal to the opposite side CB. But DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points E and P together by a straight line. By joining points E and P, we get peripheral angle APE. This is peripheral angle APE that subtends, peripheral angle APE subtends on AE, that is the diameter of this semicircle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So repeat quickly rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing you have a circle. AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore this peripheral angle ACB must be equal to 90 degrees in size according to this rule 7. Actually, we already implemented rule 7 in our drawing. Why? Because in our drawing we have peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and therefore according to rule 7, peripheral angle APE must be equal to 90 degrees in its size. We define this angle as alpha, and we focus on the right small triangle APE. In this right small triangle APE, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we prove that the big triangle ABC, the big right triangle ABC, is similar to this one right triangle APE. So I write it down. We prove that the big triangle ABC is similar to this small right triangle APE. So why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to the small right triangle APE. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to this angle, angle A, since it belongs to the big right triangle ABC, it will be defined as angle CAB. And angle A equals to itself. So if we relate to this angle A, since it belongs to the right triangle APE, it will be defined as angle PAE. So repeat again. This equation means that angle A equals to itself. We just called to angle A two different names. Angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. Actually, this is angle ABC in the right mid triangle ABC, and it is equal to this angle, that is actually angle APE in the right small triangle APE. So repeat again. Actually found out that angle ABC in the big right triangle ABC equals to angle APE in the right small triangle APE. They are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle ACB in the right big triangle ABC, and it is equal to this angle, that is actually angle PEA in the small right triangle APE. So again, we should find out that angle ACB in the big right triangle ABC equals to angle PEA in the small right triangle AP. They're both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we found out that all the figures of the big right triangle ABC are correspondingly equal to all the figures of this small right triangle APE, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If I found out that the right big triangle ABC is similar, this is the sign of similar, to the right small triangle APE according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side AP of the right small right triangle APE over side AB of the big right triangle ABC is equal to side AE of the small right triangle APE over side AC of the big right triangle ABC. So if it again, we will derive that side AP of the small right triangle AP over side AB of the big right triangle ABC equals to side AE of the small right triangle AP over side AC of the big right triangle ABC. AP equals to 6 units in its length according to what is given as the question, over AB. AB is the missing side, so we leave it as it is. And it is equal to AE. AE is the diameter of this semicircle. This is equal to 2x units. Over AC. AC in total equals to 6 plus 5, that is 11. So in total, if we found out that 6 over AB equals to 2x over 11. Here we cross multiply this equation, and we get that 6 times 11 is 66, and it is equal to 2x times AB. So 66 equals to 2x times AB. Here we will divide this equation by 2, and we get that 66 over 2 is 33, is equal to 2x over 2 is x, so in total this expression equals to x times AB. So if we found out that 33 equals to x times AB, here we will divide this equation by x, and finally we get that AB equals to 33 over x units. So if we found out that side AB of rectangle ABCD is equal to 33 over x units. Our mission is to find out the area of this rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. And again, the area of any rectangle equals to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is CB. So in total, we found out that the area of rectangle ABCD equals to AB times CB. AB is 33 over x, and CB equals to x. So in total, we should find out that the area of rectangle ABCD equals to 33 over x times x. We have x in the numerator and x in the denominator, so x will get present, and the left only will be 33. Now if we found out that the area of this rectangle ABCD, that is the area that we are looking for in this question, is equal to 33 square units. So write it down. If we found out that the area of rectangle ABCD is equal to 33 square units. And that is the answer to the question. So we finish with the first question. In the next step, I will present to you the second question and resolve the second question of this lecture. In the second question, our mission is to find out the area of this ring shape. So, in the drawing, we have square ABCD. In addition, know that this is line segment BP, that is equals to line segment PC. And finally, this is triangle POC. The size of this triangle POC is 5 square units. Again, our mission is to find out the area of this ring shape. First of all, we define the length of this line segment BP as A. But it is given as a question that BP equals to PC. But BP is A, therefore PC must be also equal to A. We also know that the opposite, all the sides of any square are equal to each other. So in square ABCD, side BC equals to A plus A, that is 2A. So the opposite side AD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define this, the size of this angle is theta, then the size of this angle must be also equal to theta, because they are equal to each other according to the rule that I mentioned. The vertex angles are equal to each other. You also know that the opposite sides of a square are parallel to each other. So in square ABCD, side AD is parallel to the opposite side BC. So those two angles are defined as alternating angles, and they are located between the parallels AD and BC. And according to Rule 15, alternating angles between parallel lines are equal to each other. So those two alternating angles that are located between the parallels AD and BC must be equal to each other in their sizes. So if the size of this angle is beta, then the size of this angle must be also equal to beta, because they are equal to each other according to Rule 15. Likewise, those two angles are also defined as alternating angles. And those two alternating angles are located between the same parallels AD and BC. And therefore they must be equal to each other according to Rule 15. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to Rule 15. So in total, we found out that those two triangles are similar to each other according to angle similarity rule. That is to say, in both sides we have angle theta, in both triangles we have angle theta, in both triangles we have angle beta, in both triangles we have angle alpha. Therefore, those two triangles are similar to each other according to angle similarity rule. So I write it down. Actually found out that this big triangle ADO is similar, this is the sign of similar, to this one triangle COP. According to angle similarity rule. According to angle similarity rule. So because of the fact that those two triangles are similar to each other, we can implement the Rule 22 that relates to similar triangles. So I read Rule 22 and we implement Rule 22 on those two similar triangles. According to Rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have those two triangles, triangle ABC and triangle DEF, that are similar to each other. And according to this rule, Rule 22, the ratio between the areas of those two triangles, that is to say the area of this triangle ABC over the area of this triangle EDF, is equal to the square of the ratio of their corresponding sides. So what is the square of the ratio of their corresponding sides? On those two triangles ABC and DEF, side AC is the corresponding side of side DF. Likewise, side AB is the corresponding side of side DF, and finally, side CB is the corresponding side of side DF. So side AC is the corresponding side of side DF. So what is the square of the ratio of those two corresponding sides? It's actually AC over DE squared. Okay? The square of the ratio of those two corresponding sides is AC over DE squared. So in total, we found out that the ratio between the areas of those two similar triangles, that is to say the area of triangle ABC over the area of triangle EDF, is equal to the square of the ratio of their corresponding sides, that is to say AC squared over AC over DE squared. Likewise, side AB is the corresponding side of side DF. So the square of the ratio of those two corresponding sides is of course AB over DF squared. AB over DF squared. And finally, side CB is the corresponding side of side EF. Therefore, the square of the ratio of those two corresponding sides is of course CB over EF squared. CB over EF squared. Okay, so the square of the ratio between their areas is equal to the square of the ratio of their corresponding sides. So we can implement Rule 22 in our drawing. Why? Because in our drawing we have already found out that those two triangles are similar to each other. So according to Rule 22, the square of the ratio between the areas of those two similar triangles, what is the ratio of the areas of those two similar triangles? It is actually the area of the big triangle ADO over the area of triangle COP. The area of triangle DAO over the area of the small triangle, triangle COP. So this expression is the ratio between the areas of the two similar triangles, and that ratio is equal to the square of the ratio of their corresponding sides. So what is the square of the ratio of those of their corresponding sides? Here side AD is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that side AD in triangle ADO is in front of angle theta, and side PC in triangle POC is also in front of angle theta. Therefore, side AD in triangle ADO is the corresponding side of side PC in the small triangle POC. So what is the square of the ratio of those two corresponding sides? It is of course AD over PC squared. AD over PC squared. So we found out that the ratio between the areas of those two similar triangles is actually the area of triangle over the area of triangle COP is equal to the square of the ratio of their corresponding sides. That is to say AD over PC squared. So this equation is the implementation of Rule 22 in our drawing, in our two similar triangles DAO and COP. The area of this big triangle DAO is unknown, so we leave it as it is. It is the area of triangle DAO over the area of the small triangle COP. The area of this small triangle COP is equal to 5 square units in its size according to what is given us the question. So we substitute the area of the small triangle COP by 5, and it is equal to AD over PC squared. AD is 2A, PC is A, so it is AD over PC squared. That is to say it is 2A over A squared. We have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2 squared. 2 squared is of course 4. So in total we can find out that the area of the big triangle DAO over 5 equals to 4. So here we multiply this equation by 5, and we get that the area of the big triangle DAO is equal to 5 times 4, that is 20 square units. So we found out that the area of this big triangle DAO is equal to 20 square units. Because of the fact that the big triangle DAO is similar to this small triangle COP, the following relationship exists between their sides. Side DA of this big triangle DAO over side PC of this small triangle POC is equal to side AO of this big right triangle AOD over side OC of this small triangle POC. And again, from the fact that those two triangles are similar to each other, we derive that the following relationship exists between their sides. That side DA of the big triangle ADO over side PC of the small triangle POC equals to side AO of the big triangle DOA over side OC of the small triangle COP. DA is 2A over PC. PC is A. And it is equal to AO over OC. AO over OC. In this side of the equation we have A in the numerator and A in the denominator, so A will get cancelled and we left only with 2 equals to AO over OC. So here we multiply this equation by OC and we get that 2 times OC is equal to AO. We will define the length of side OC as B. That is to say, side OC equals to B units in its length according to our definition, and we substitute OC in this equation by B, and we get that 2B equals to AO. So we found out that if the length of this side OC is B, then the length of this side AO is 2B. That is to say, AO is twice as long as OB. Okay, so in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is Rule 23. this is triangle ABC that could be any triangle. This triangle ABC, we draw the red line segment AP by drawing the red line segment AP. We divided this big triangle ABC into two small triangles. The first triangle is triangle ABP and the second triangle is triangle APC. And rule 23 is about those two small triangles that were created by drawing line segment AP in triangle ABC. And according to this rule 23, the ratio between the areas of those two small triangles, that is actually the area of triangle ABP over the area of triangle APC, is equal to the ratio between their corresponding bases. The base of triangle APC and the base of triangle ABP is BP, and the base of this triangle APC is PC. And the ratio between their corresponding bases is of course BP over PC. So, repeat again, according to the new rule 23, the ratio between the areas of those two small triangles, that is actually the area of triangle ABP over the area of triangle APC, is equal to the ratio between their corresponding bases, that is actually BP over PC. Okay, so how we arrive to this equation, to this equality? Why? Because the area of this triangle ABP, we have in the equation the area of triangle ABP. But what is the area of triangle ABP? It is equal to the base of the triangle that is BP times the height that is edge over 2. So in total, the area of this triangle ABP is equal to the base BP times the height that is edge over 2. Okay. Likewise, the area of this small triangle APC, it is equal to the base that is PC times the height edge over 2. So this is the base PC times the height edge over 2. Both triangles have the same height that is edge. Okay? And what is the ratio between the areas of those two triangles? It's actually the area of triangle ABP, that is BP times edge over 2, over the area of triangle APC, that is actually CP times edge over 2. Okay, so the ratio between the areas of those two small triangles is the ratio between those two expressions. So here we have edge in the numerator and edge in the denominator, so edge will get cancelled, and we also have 1/2 in the numerator and 1/2 in the denominator, so 1/2 also will get cancelled, and we're left only with BP over CP. So in total, we have found out that the ratio between the areas of those two small triangles is equal to BP over CP. BP is the base of triangle ABP, and PC is the base of this triangle APC. And the ratio between their bases is of course BP over PC. So the ratio between the areas of those two small triangles is equal to the ratio between their bases, that is BP over CP. And because of the fact that triangle ABC could be any triangle, this equation is true for any triangle. Okay, so we implement the new rule 23 in our drawing. In our drawing, we have the right big triangle ADC. This right big triangle ADC, we have here line 7 DO. Line 7 DO divides the big right triangle ADC into two parts, into two small triangles. The first small triangle is ADO and the second small triangle is ODC. Okay, so all the requirements of Rule 23 are satisfied, and therefore we can implement here Rule 23. Rule 23 talks about those two small triangles that were created by drawing line 7 DO and triangle ADC. And according to Rule 23, the ratio between the areas of those two small triangles that were created by drawing line 7 DO and triangle ADC, the ratio between the areas of those two triangles. So what is the ratio between the areas of those two triangles? It is actually the area of triangle ADO over the area of this small triangle, ODC. And again, this expression is the ratio between the areas of those two small triangles. It's actually the area of triangle ADO over the area of triangle ODC. That ratio is equal to the ratio between their corresponding bases. According to Rule 23, the base of this triangle ADO must be AO, and the base of this triangle DOC must be OC. And the ratio between their bases is, of course, AO over OC. AO over OC. So this equation is the implementation of Rule 23 in our right triangle, triangle ADC. And according to this equation, according to Rule 23, the ratio between the areas of those two small triangles is actually the area of triangle ADO over the area of triangle ODC equals to the ratio between their bases. That is to say, it is AO over OC. Okay? Because the base of triangle ADO must be AO, and the base of triangle DOC must be OC. So the ratio between the bases of the small triangles, that is the area of triangle ADC over the area of triangle ODC, equals to the ratio between their corresponding bases. This is AO over OC. Okay? Because of the fact that triangle, this is triangle ABC, that it could be any triangle, and therefore the same equation will be true in the right triangle ADC. Okay, so we don't have to prove that this equation is true also in this triangle ADC. So the area of triangle ADC, ADO, this letter is O. The area of triangle ADO is 20, so substitute the area of triangle ADO by 20 over the area of triangle ODC. The area of this triangle ODC is unknown, so leave it as it is. This is the area of triangle ODC. So 20 over the area of triangle ODC equals to AO over OC. AO is 2B, and OC is B. So in total, we found out that 20 over the area of triangle ODC equals to 2B over B. We have B in the numerator and B in the denominator, so B will get cancelled, and we left only with 2. So in total, we found out that 20 over the area of triangle ODC is equal to 2. So here we multiply this equation by the area of triangle ODC. And we get that 20 equals to 2 times the area of triangle ODC. And we found out that 20 equals to 2 times the area of triangle ODC. Here we divide this equation by 2, and finally we get that the area of the small triangle ODC is equal to 20 over 2, that is 10 square units. So we found out that the area of this triangle ODC is equal to 10 square units. It is very easy to see from the drawing that the big right triangle ABC can point to this big right triangle ADC according to side rule. So why those two triangles can point to each other? First of all, we know that ABCD is a square, so all of its sides are equal to each other. So why those two triangles can go into each other? First of all, side AB of triangle ABC is equal to side DC of triangle ADC. because ABCD is a square. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC for the same reason. And finally, AC is a common side that belongs to both triangles. So can I know that AC equals to itself? It's a common side that belongs to both triangles. So in total, we actually found out that those two right triangles can point to each other according to side rule. So write it down. So we found out that the big right triangle ABC congruent, this is the sign of congruent, to the right big triangle ADC according to side rule. And from the fact that those two right big triangles can go into each other, you will derive that they have also the same areas. Why? Because any two triangles that can go into each other, they must have also the same areas. Therefore, the area of triangle ABC is equal to the area of triangle ADC. So the area of the big right triangle ABC is equal to the area of the big right triangle ADC. But from the drawing, it is very easy to see that the area of this big right triangle ADC in total it is equal to 20%, that is 30 square units. So you can write here that the area of the big right triangle ADC is equal to 30 square units. And from this equation, the area of triangle ABC equals to the area of triangle ADC equals to 30 square units. We derive that the area of triangle ABC is also equal to 30 square units. So the area of triangle ABC is also equal to 30 square units. That is from one side, but from the other side, what is the area of this big right triangle ABC? The area of this big right triangle ABC is equal to the area of this green shape plus the area of this triangle COP. So we define the area of this green shape as x, that is to say, the area of the green shape is equal to x square units according to our definition. So it is x plus 5, because 5 is the area of this triangle POC. So in total, from the other side, the area of triangle ABC is equal to x plus 5 square units. So from the other side, the area of triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 is equal to 30. So here we subtract 5 from this equation, and we get that x equals to 30 minus 5 is 25 square units. But x is the area of the green shape, that is the area that we are looking for in this question. So in conclusion, we found out that the area of the green shape is equal to 25 square units. And that is the answer to the second question. Again, we found out that the area of this green shape, that is the area that we are looking for in this question, is equal to 25 square units. So finished with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our mission in the first question is to find out the area of this rectangle ABCD. So in the domain we have rectangle ABCD. Inside this rectangle we have this semicircle. In addition, we know that this is called AP, that is equal to 6 units in its length. This is line 7 PC, that is equal to 5 units in its length. Again, our mission is to find out this big rectangle ABCD. So first of all, those 4 angles, they are all right angles, because all the angles inside any rectangle are right angles. So those 4 angles are all right angles. So in the next step, we define the center of this semicircle. This point is point O. We define the radius of this semicircle as x. We define the point of tendency of tangent DC with this semicircle. This point is point M. We define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. So point O is the center of this semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, that is equal to x. Unit in itself according to our definition. Likewise, OE is also the radius of the semicircle, that is equal to x. In the next step, we join points O and M together by straight line. OM is of course the radius of this semicircle, that is equal to x. And because of the fact that the radius OM that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So by doing this construction, we created the small quadrilateral DMOA. Inside this small quadrilateral DMOA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this 4 facing angle must be equal to 90 degrees in its size. So inside the small quadrilateral DMOA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this right angle if not a square. So we relate to this small quadrilateral DMOA as a rectangle because it has 4 right angles. But we also know that the opposite sides of the rectangle are equal to each other. So in the small rectangle DMOA, side MO must be equal to the opposite side DA. But MO is x, therefore the opposite side DA must be also equal to x units in its length. Likewise, in the big rectangle ABCD, the opposite sides must be also equal to each other. That is to say, side DA must be equal to the opposite side CB, but DA is x, therefore the opposite side CB must be also equal to x units in its length. In the next step, we join points P and E together by straight line. By joining points P and E, we created the peripheral angle APE. This is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and we know that any peripheral angle that subtends on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. Therefore, peripheral angle P is equal to 90 degrees in its size, according to rule 7. In the next step, we find this angle as alpha, and we focus on the right small triangle AP. In the right small triangle AP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the right big triangle ABC is similar to this right small triangle AP. So why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. Angle A belongs to the big right triangle ABC, and angle A also belongs to the small right triangle APE. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So in total, we should find out that all the triangles of the right big triangle ABC are correspondingly equal to all the triangles of this right small triangle AP. And therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. That side AP of the right small triangle APE over side AB of the right big triangle ABC is equal to side AE of the right small triangle AP over side AC of the right big triangle ABC. So repeat again. We derive that side AP of the right small triangle APE over side AB of the right big triangle AB is equal to side AE of the right small triangle APE over side AC of the right big triangle ABC. AP is equal to 6 units in itself, according to what is given as the question, over AB. AB is the missing side, so we limit as it is, and it is equal to 2AE. AE is the diameter of this semicircle, it is equal to 2x over AC. AC in total it is 6 plus 5, this is 11. So in total we should find out that 6 over AB equals to 2x over 11. Here we cross multiply this equation, and finally found out that 6 times 11 is 66, and it is equal to 2x times AB. Here we divided this equation by 2, and finally found out that 66 over 2 is 33, and this equals to 2x over 2 is x. So in total this expression equals to x times AB. Here we divided this equation by x, and finally found out that AB equals to 33 over x. So if we found out that the length of this side AB of rectangle ABCD is equal to 33 over x units. Our mission is to find out the area of this big rectangle ABCD. So we have to find out the area of rectangle ABCD. So what is the area of rectangle ABCD? Actually, we know that the area of any rectangle is equal to the length of the rectangle times the width. Okay, the area of any rectangle is equal to the length of the rectangle times the width. And therefore, the area of this rectangle ABCD must be equal to the length of this rectangle ABCD times the width. The length of this rectangle ABCD is AB, and the width is BC. So therefore, the area of this rectangle ABCD must be equal to AB times BC. And again, the area of rectangle ABCD must be equal to the length AB times the width, that is CB. But AB is 33 over x, and CB is x. CB is x. So in total, we shall find out that the area of rectangle ABCD is equal to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So in total, we shall find out that the area of this rectangle ABCD, this is the area that we are looking for in this question, is equal to 33 square units. So we finish with the first question. In the next step, I presented to you the second question, and you solve the second question of this lecture. Our mission in the second question is to find out the area of this green shape. So in the drawing, we have square ABCD, this is square ABCD. Also know that this is line 7 BP, this is equal to line 7 PC. And finally, we also know that this is triangle POC, that is equal to 5 square units in its size. Again, our mission is to find out the area of this green shape. So first of all, we define the length of this line 7 BP as A. And because of the fact that BP equals to PC, PC must be also equal to A. And because of the fact that ABCD is a square, all of its sides must be equal to each other. But the length of side BC of square ABCD is A plus A, that is 2A. Therefore, the opposite side AD must be also equal to 2A units in its length. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is theta, then the size of this angle must be also equal to theta, because they must be equal to each other according to the rule that I mentioned. We also note that the opposite sides of a square are parallel to each other. So in square ABCD, side AED is parallel to the opposite side BC. Those two angles are defined as alternating angles, and they are located between the two parallel lines AED and BC. And therefore, they must be equal to each other according to Rule 15 that said that alternating angles between parallel lines are equal to each other. So those two angles must be equal to each other according to rule 15. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they must be equal to each other according to rule 15. Likewise, those two angles are also defined as alternating angles and are located between the same parallel lines AD and BC, and therefore they must be equal to each other according to rule 15. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they must be equal to each other according to rule 15. Okay, so in total we found out that those two triangles, they are similar to each other according to angle similarity rule. That is to say, in both triangles we have angle theta, in both triangles we have angle beta, and in both triangles we have angle alpha. Therefore, those two triangles are similar to each other according to angle similarity rule. And therefore, we can actually implement, so I repeat again, if we found out that the big right triangle ADO is similar to the small right triangle COP according to angle similarity rule. And therefore, we can implement here rule 22. Rule 22 relates to similar triangles, and because of the fact that those two triangles are similar, we can implement here rule 22. So I'll repeat quickly on rule 22. According to rule 22, the ratio of the areas of similar triangles is equal to the square of the ratio of their corresponding sides. So in the drawing we have those two triangles that are similar to each other. That is to say, this is triangle ABC that is similar to this triangle DEF. And according to this rule 22, the ratio between the areas of those two similar triangles, that is to say, what is the ratio between the areas of those two similar triangles? It is actually the area of triangle ABC over the area of triangle EDF. That ratio is equal to the square of the ratio of their corresponding sides. What is the square of the ratio of their corresponding sides? Side AC is the corresponding side of side DE. Side AB of triangle ABC is the corresponding side of side DF. And side CB is the corresponding side. Side CB in triangle ABC is the corresponding side of side EF of triangle DF. So side AC is the corresponding side of side DE. And the square of the ratio of their corresponding sides, that is actually AC over DE squared. AC over DE squared. Likewise, side AB is the corresponding side of side DF. And the square of the ratio of those two corresponding sides is of course AB over DF squared. AB over DF squared. And finally, side CB is the corresponding side of side EF. And therefore, the square of the ratio of those two corresponding sides is of course CB over EF squared. So in total, we found out that according to rule 22, the ratio between the areas of those two small triangles, that is to say it is the area of triangle ABC, what is the ratio of the areas of those two small triangles? It is the area of triangle ABC over the area of triangle EDF. That ratio is equal to the square of the ratio of their corresponding sides. So we can actually implement rule 22 in our drawing. Why? Because in our drawing, we have already found out that those two triangles are similar to each other. So according to rule 22, the ratio between the areas of those two similar triangles, what is the ratio between the areas of those similar triangles? It is actually the ratio, the area of triangle AOD over the area of triangle POC. Repeat again, the ratio between the areas of those two similar triangles, it is equal to the area of triangle AOD over the area of triangle COP. That ratio is equal to the square of the ratio of their corresponding sides. On those two similar triangles, side AD is the corresponding side of side PC. Why side AD is the corresponding side of side PC? Because of the fact that side AD is in front of angle theta in triangle ADO. Likewise, side PC is in front of the same angle theta in the small triangle POC. Therefore, side AD is the corresponding side of side PC. And the square of the ratio of those two corresponding sides is of course AD over PC squared. Again, the square of the ratio of their corresponding sides is AD over PC squared. So the ratio between the areas of the two similar triangles is equal to the square of the ratio of their corresponding sides. The area of triangle DAO, the area of this big triangle DAO is unknown, so leave it as it is. over the area of the small triangle COP. It is given us the question that the area of this small triangle POC is equal to 5 square units. Therefore, we substitute the area of triangle COP by 5, and it is equal to AD over PC squared. AD is 2A, PC is A. AD is 2A, PC is A, and we have to square it. We squared it here. We have A in the numerator and A in the denominator, so A will get cancelled, and we left only with 2 squared, that is 4. So in total, we found out that the area of the big triangle DAO over 5 equals to 4. Again, the area of the big triangle DAO over 5 equals to 4. Here we multiplied this equation by 5, and we found out that the area of the big triangle DAO equals to 5 times 4, that is 20. That is to say, we found out that the area of this big right triangle AOD is equal to 20 square units. Because of the fact that those two triangles are similar to each other, the following relationship exists between their sides. Side AD of this triangle ADO over side PC of this triangle POC is equal to side AO of this triangle ADO over side OC of this triangle POC. Repeat again. Side AD of triangle AOD over side PC of triangle POC is equal to side AO of triangle AOD over side OC of triangle POC. AD is 2A and PC is A. Again, AD is 2A and PC is A. And it is equal to AO over OC. We have A in the numerator and A in the denominator, so A gets cancelled, and we have to leave with 2. So 2 equals to AO over OC. We multiply this equation by OC, and finally found out that 2 times OC equals to OA. Here we define the length of side OC as B. Then we substitute OC by B in this equation, and finally found out that 2B equals to AO. That is to say, if we define the length of this side OC as B, then the length of side OA must be equal to 2B. That is to say, OA is twice as long as OB. Okay, so in the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule 23. This is triangle ABC that could be any triangle. In this triangle ABC, if we draw the red line segment AP, it will divide this triangle ABC into 2 smaller triangles. The first small triangle is triangle ABP, and the second small triangle is triangle APC. Rule 23 is about those 2 small triangles that were created by drawing line segment AP in triangle ABC. And according to this rule, rule 23, the ratio between the areas of those 2 small triangles is equal to the ratio between their corresponding bases. So what is the ratio between the areas of those 2 small triangles? It is actually the area of this triangle ABP over the area of this triangle APC. What is the area of this triangle ABP? It is equal to the base of the triangle that is BP times the height that is edge over 2. Repeat again, the area of this triangle ABP equals to the base BP times the height edge over 2. Likewise, the area of this triangle APC is the base PC times the height edge over 2. The base PC times the edge over 2. So both triangles have the same height, that is edge. So what is the ratio between the areas of those 2 triangles? It's actually the ratio between those 2 expressions, because this expression is the area of triangle ABP, and this expression is the area of this triangle APC. So the ratio between the areas of those 2 triangles is the ratio between those 2 expressions. And so I copied those 2 expressions here, and the ratio between the areas of those 2 triangles is the ratio between those 2 expressions. We have 1/2 in the numerator and 1/2 in the denominator, so 1/2 will get cancelled. We have edge in the numerator and edge in the denominator, so also will get cancelled. And we have to live with BP over CP. So in total, we found out that the ratio between the areas of those 2 triangles, that is actually the area of triangle ABP over the area of triangle APC, is equal to BP over CP. BP is the base of triangle ABP, and PC is the base of triangle APC. And the ratio between the bases is, of course, BP over PC. So in total, we found out that the ratio between the areas of those 2 small triangles, that is the area of triangle ABP over the area of triangle APC is equal to the ratio between their bases, that is actually BP over CP. And because of the fact that ABC would be any triangle, we can implement rule 23 in any triangle. So we implement rule 23 in this big right triangle ADC. In this big right triangle ADC, we have line segment OD that divides the big right triangle ADC into two smaller triangles. So all the requirements of rule 23 are satisfied, and therefore we can implement rule 23. According to rule 23, the ratio between those two, the ratio between the areas of those two small triangles that were created by drawing line segment OD in triangle ADO, the ratio between the areas of those two small triangles is equal to the ratio between their corresponding bases. The base of this triangle ADO is AO, and the base of this triangle OCD is OC. So in total, we found out that according to rule 23, the ratio between the areas of those two small triangles is equal to AO over OC. That is the ratio between their corresponding bases. So according to rule 23, the ratio between the areas of the two small triangles is the area of triangle ADO over the area of triangle ODC. Again, it is the area of this triangle ADO over the area of triangle ODC. That is the ratio between the areas of those two small triangles, and that ratio is equal to the ratio between their corresponding bases. This is actually AO, this is the base of triangle ADO, and OC is the base of triangle OCD. So the ratio between their bases is AO over OC. Again, the ratio between their bases is AO over OC. So this equation is the implementation of rule 23 in our drawing. We have only found out that the area of triangle ADO, the area of this big triangle ADO is 20. So we substitute the area of triangle ADO by 20 over the area of triangle ODC. The area of this triangle ODC is unknown, so we left it as it is. So in total, we actually found out that 20 over the area of triangle ODC equals to AO over OC. AO is 2B and OC is B. Again, AO is 2B and OC is B. We have B in the denominator and B in the denominator, so B will get cancelled, and we left only with 2. So in total, we actually found out that 20 over there of triangle DOC is equal to 2. Here we multiplied the area of this triangle DOC, we multiplied this equation by the area of this triangle DOC, and finally found out that 20 equals to 2 times the area of triangle DOC. Here we divided this equation by 2, and finally found out that the area of this triangle DOC is equal to 20 over 2, that is 10 square units. Again, the area of this triangle DOC is equal to 10 square units. From the drawing, it is very easy to see that this right big triangle ABC can go into this right big triangle ADC according to side rule. So why those two triangles can go into each other? First of all, because of the fact that ABCD is a square, all of its sides are equal to each other. So why those two right triangles can go into each other? First of all, side AB of triangle ABC is equal to side DC of triangle ADC, because of the fact that ABCD is a square. Likewise, side BC of triangle ABC is equal to side AD of triangle ADC for the same reason. And finally, side AC is a common side that belongs to both triangles. So we can write down that AC equals to itself as a common side that belongs to both triangles. So in total, we actually found out that those two triangles can go into each other according to side rule. Why? Because of the fact that all the sides of the right big triangle ABC are correspondingly equal to all the sides of the right big triangle ADC. So in total, we found out that triangle ABC congruent, this is the sign of congruent, to the right big triangle ADC according to side rule. And from the fact that those two right triangles are congruent to each other, we derive that they have also the same areas. Why? Because of the fact that any right triangles that can go into each other, they must all have the same areas. Therefore, the area of triangle ABC must be equal to the area of triangle ADC because they can go into each other. But the area of this triangle ADC from the drawing is very easy to see that the area of this triangle ADC is equal to 20 plus 10, that is 30 square units. So you can write here that the area of this triangle ADC is equal to 30 square units. And from this equation, the area of triangle ABC equals to the area of triangle DC equals to 30, we derive that the area of triangle ABC is equal to 30 square units. That is from one side. But from the other side, what is the area of this triangle ABC? The area of this triangle ABC is of course equals to the area of this green shape plus the area of this triangle POC. So we define the size the area of this green shape as x, that is why it is equals to x square units according to our definition, plus the area of this triangle POC, that is 5 square units according to what is given as the question. So in total, the area of this triangle ABC from the other side is equal to x plus 5 square units. So from the other side, the area of triangle ABC is equal to x plus 5 square units. And from this equation, x plus 5 equals to the area of triangle ABC equals to 30. We will derive that x plus 5 equals to 30. So here we subtracted 5 from this equation and finally found out that x equals to 30 minus 5, that is 25 square units. X is the area of this green shape, that is equals to 25 square units. So in total, the answer to this question is that the area of this green shape, that is the area that we are looking for in this question, is equal to 25 square units. Okay, thank you very much.